Welcome back for our second video in 9.2, where we are introducing the idea of series and convergence of series. So this question of adding up all the terms of a sequence, which we defined in 9.1, and seeing if we get something finite in return. So in the previous video, we looked at what it means for a series to converge. We wrote some definitions. We looked at the partial sums, remember? And we create a sequence of partial sums and hope that we could find a pattern, and then take the limit of those partial sums to get the sum as a whole. Now, we did that in one example, and then we also saw, well, there's some special types of series in which we can find those partial sums. We can find that pattern, and the first one we looked at was telescoping. This idea of cancellation, infinite cancellations, where you're only left with a handful of terms, and therefore can take a limit of the partial sums and hopefully get an answer. The other type of special series we're going to look at, aside from telescoping, is what we call a geometric series. Now, a geometric series is interesting because in this case, we're not going to have a bunch of cancellation. We are actually adding up infinitely many things. And what it is it's of the form AR to the n. N is the variable here, right? N is the exponent. So these are like exponential functions that you learn in algebra and also in Calc 1. What exponential functions look like, right? You either have exponential growth or decay. That's going to be important to remember. And so you're looking at powers of r, some base r. That's your base of your exponential. So like 2 to the n or 1/2 to the n, right? R is a constant. And then maybe you have some scale of that exponential function in front. So a is just some other constant as well. We could possibly scale it. So AR to the n. And then the other thing that makes geometric series a little bit different in their standard form is, remember, sequences are functions on the natural numbers. You start your first natural number being the number 1. Geometric series are technically defined as starting at 0. So even though 0 is not a natural number, we can start wherever. In this case, geometric series start at the number 0. So the first number you'll plug in is 0 for the exponent. Anything to the 0 power is 1, and so 1 times a is just a. So that's why the first term is just a, no r. Then when n is 1, now it's AR, n is 2, AR squared, n is 3, AR cubed, so on. And therefore, it's a little bit tricky, so we just have to be careful when we write out partial sums. And so if we think about what a geometric series looks like, given a geometric sequence, we're now adding it all up, geometric series. And we start listing out the partial sums. It's the sum of the first n terms. And so the sum of the first term is the actual 0th term, right, when you plug in 0a. The sum of the first 2 terms would be plugging in 0 and plugging in 1. The sum of the first 3 terms, ... The sum of the first n terms would then be a plus AR out to AR to the, not n, but n minus 1. And that's because n terms, including the 0 term, would then only get me out to the n minus 1th power because of the starting at 0 thing. So we're kind of taking a step back. And so we write out the nth partial sum. And of course, there's, we see a pattern. We're adding the powers of r. But there's no way to get a general formula, right? Working with this ... doesn't really allow me to then take a limit as n goes off to infinity. And so we'd like to get a nice, concise formula in terms of an n that describes the nth partial sum, and therefore we can take a limit and figure out the convergence or divergence of a geometric series, like we did with telescoping. And so we're going to play a little game here. We're going to try to manipulate the way this formula looks. And don't worry about why I'm doing it, but I'm going to take the nth partial sum formula and multiply it by r. Therefore, bumping up everything by a power of r. So now it's AR plus AR squared plus ... now out to AR to the n. We bumped up everything. So the term right before this is now AR to the n minus 1, and we bumped up the last one to AR to the n. Right? We've multiplied everything by r. So distributed through bumps up all the powers. And then what I'm going to do is I'm going to take the nth partial sum and subtract r times the nth partial sum, because I like this idea of telescoping, of cancellations that we saw in the last special series. And what's great about this is when I take the nth partial sum and I subtract the r times the nth partial sum, a won't cancel, AR minus AR go away, AR squared minus AR squared go away. Even AR n minus 1 cancels with the term right before this one, which is AR n minus 1. And then all I'm going to be left with is minus this last term, AR to the n. Now what's great about this is I can solve this for Sn. I can factor out a 1, or factor out the Sn, getting 1 minus r, factor out the a, giving me this. And I can divide both sides by 1 minus r. The reason I just put it underneath the a, I could put it over the whole thing, there's no difference. I put it here because remember a and r are just constants, so this is just some sort of number. It has nothing to do with n. The only thing that's important here in terms of the limit is that term. And now I have a nice clean version of the nth partial sum in terms of n without this whole dot 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 with some unknown number of terms. And now that I have this, now remember we take the limit of the partial sums to try to figure out, well, what's going on if we add up everything. So what do we need to take the limit of? This whole thing here. Remember that a and r are constant, so this is just a number. This can be pulled out of the limit. And we're left with this. And now just comes the important fact to remember that these are exponential functions, r to the n. R is just a number, so like 2 to the n, or 1/2 to the n. And we know things about exponential functions. We'll break up into 2 cases depending on r. If the value of r is bigger than 1, 2, 3, even 3/2, bigger than 1, this is exponential growth. This function will blow up, right? 2, if we're looking at powers of 2, that number is just getting larger and larger. And therefore, when I take n off to infinity, this number will blow up to infinity, and 1 minus infinity will be negative infinity. And so this thing will blow up. So if the value of this number, absolute value of it, is bigger than 1, then what? Then the limit, as n goes to infinity, of 1 minus r to the n does not exist. And so the limit of the partial sums doesn't exist, and so the series diverges. The other option is that r is less than 1. If the value of r is less than 1, then actually this is exponential decay, like 1/2 to the n, think of. Powers of 1/2. So 1/2, 1/4, 1/8, 1/16. Wait a minute. If I look at powers of numbers less than 1, that's exponential decay. That's actually going to 0. And then the second term is going to 0. 1 minus 0 is 1, which implies, of course, we get something finite. So now this series converges. And what is the sum? Remember, this is 1, but remember it's 1 times this. And so the sum is a over 1 minus r. A over 1 minus r times 1. And so with geometric series, we have the 2 situations. We have when the value of r is bigger than 1, when value of r is less than 1. What about when it equals 1? Well, if the value of r equals 1, let's just look back at this definition. If r is 1, then 1 here, 1 squared is 1, 1 cubed is 1. So then I'm just adding up a forever. A plus a plus a plus a, right? If r is 1, this is just a every single time. A plus a plus a forever. If you think about that, a plus a plus a is not 0, right? We're assuming this is not a 0 entry. Otherwise, right, this is not a really series to begin with if a is 0. So assuming a is not 0, now I'm adding a number that's not 0 forever. Well, if you think back to our first definition in series, if the thing I'm adding up doesn't go to 0, it can't converge. So specifically, if I'm adding up a non-zero number forever, it definitely will not converge. And so in that case, even if r is greater or equal to 1, it will fall into this category of the limit not existing and the series diverging. And so what is our conclusion with geometric series? Given a geometric series, ar to the n, it will converge if the value of r is less than 1. It will diverge if the value of r is bigger than or equal to 1. And of course, if it converges, what is the sum? A over 1 minus r. What is the actual sum of the series if it's finite? And so geometric series are also a nice understood series because we can have a formula for the partial sums. Of course, we have to do a little more work here because we have to take a limit of something that's not as clear, right? We have to think it in 2 cases, depending on r. But in either case, depending on what r is, we have an answer for geometric series. And so this is how we work with geometric series. So let's look at some examples of geometric series. Let's get ourselves used to the idea of geometric series. And so say we want to add up 2 times 1/3 to the n. This is geometric. We have AR to the n. We have an exponential function scaled by 2. It fits the form of a geometric series. A is 2, r is 1/3. And sure enough, it fits the bill of r being less than 1, right? The value of r is 1/3, which is less than 1. So this implies that the series converges, so we will get a finite answer. What is my solution? We actually have a very explicit formula. We don't even need to take a limit. It's a over 1 minus r. So it's 2 over 1 minus 1/3. So 2 over 1 minus 1/3 is 2/3. Multiplying by the reciprocal, we get 2 times 3/2, which is 3. So this series converges and the sum is 3. Let's look at another example. E to the minus n. And at first you're thinking, well, e to the minus n, wait a minute, this has a negative exponent. E looks like a variable. Remember, it's just a number, so we don't want to be freaked out by that. But remember, negative exponents, I can rewrite it like this. Same thing as it's reciprocal to the nth power, right? Negative means take the reciprocal. And we can rewrite it in this way. And now it fits the bill of being geometric. In this case, a is 1. Imaginary 1 there in front since there is no other number. R is 1 over e. Remember, e is a number. E is 2.7 dot 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 dot. And more importantly, 1 over 2.7 dot 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 is less than 1. So the value of 1 over e is certainly less than 1, which tells me this series converges. So not only that, now we know the sum. We have a very explicit formula. Remember, a over 1 minus r. 1 over 1 minus 1 over e. I can leave this, or I mean, we could simplify. We get 1 over common denominator of e would be this, multiplying by the reciprocal. Get that. So again, another geometric series that converges. We can talk about series that don't converge, but that's not very interesting because there's not so much to do after that. And so, example, 2 times 2/3 to the negative n. At first you're thinking, oh, 2/3, that's less than 1, it converges. But this negative n is there for a reason. If you actually look at it, negative means reciprocal. So actually this is really the series 2 times 3/2 to the n. Well, the value of r is 3/2. That's bigger than 1. This implies the series diverges. So of course it doesn't have a sum, so we're done. It blows up. There is no sum to this series. Diverges, converges. So it's really easy as long as you know what your geometric series looks like. Right? You can make it look like a geometric series. The only thing you could do here would be to just manipulate the way the series is given, so that might not look geometric right away. Remember in the telescoping one when we had the rational function that then you did partial fractions to split, and sure enough then it became telescoping. In the same way, maybe you could have something like this. N equals 0 to infinity. 3 to the n plus 1 over 5 to the n. And maybe it doesn't look geometric right away, but we can manipulate it using our knowledge of how exponentials work to write it in a geometric form. So 3 to the n plus 1, well, that's 3 to the n times 3. So my rules of exponents backwards, right? 3 to the 1, 3 to the n plus 1. I do that because then I can pull the 3 in front, and then I can use rules of exponents to combine these second terms as 3/5 all to the n. 3 to the n over 5 to the n is 3/5 to the n. And just through an easy, geometric manipulation, exponential manipulation, it's now geometric. The value of r is 3/5, which is less than 1. So this converges. And we can find the sum, a over 1 minus r. So we get 3 over 5/5 minus 3/5, so 2/5 in the bottom. And then multiplying by the reciprocal, we get 15/2. So it converges and the sum is 15/2. And so even if it doesn't look geometric right away, we can also maybe manipulate the way it looks so that it becomes geometric, just like this one. This was an easy manipulation. This one a little bit more involved. And then, we can also try to trip people up or just make them think, not that we're doing it on purpose, but just to, get some critical thinking in. We can also think about something like this. This is a geometric series. The value of r is less than 1/2. It's already written in a nice form. And so we know this series converges. The value of r is less than 1. But when we find the sum, we have to be a little bit careful because remember the sum formula implies that n starts at 0, and it does not. And so we have to re-index some things. Remember, let's think about what this is going to amount to. Let me just write out some terms really quick. This is 2 times 1/2 plus 2 times 1/2 squared plus dot, 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 dot. All right, then starts at 1. I want to rewrite this so that n starts at 0 to infinity, but then I would need to change the power of n in some way so that I still get the same sum. If I want n to start at 0, but the first term needs to be 1/2 to the 1, then that means I need to rewrite the power of n like this. That way, the series starts at 0. It has the right form for the sum, the indices. And when I plug in 0, I'm still not changing the series, right? This still times 2 times 1/2 then. If n is 0, we get 1 for the exponent. When n is 1. So they are the same. I just had to change this to be starting at 0. Now I still can't use the geometric sum formula because again, now that I fixed this issue, I've now created another issue. But now it's just a matter of rules of exponents. So even though I've created another problem, that can be fixed by, just like we did in the last example, how we split the 3 to the n plus 1 into 2 pieces. Same thing here. I can split the 1/2 to the n plus 1 into 2 pieces. Throw this 1/2 to the 1 with the constant in front. And actually that's great because then they cancel. And we get this. So this series, long story short, this series can be written as this series. And all I've done is some manipulation so that I get in the right form to fit the bill for geometric. I already knew it converged because notice r is not changing in any of this. It's just changing the index to start at 0. And in doing so, I create another problem that I had to adjust, fix. And it still converges, but now we can use our sum formula, right? So the sum is, a is now 1, r is 1/2. 1 over 1 minus 1/2. 1 over 1/2, or 2. So the sum of the series is 2. And so we just have to be mindful of keeping track that, okay, remember with geometric series, they do have to start at 0 if I want to use the sum formula, that shortcut of a over 1 minus r. And if it doesn't start at 0, we can easily fix that. Even if it started at 2 or 3, we could shift it down to 0, and then we would just need to shift our exponent up by 3. Just like we did here, right? We wanted to shift it down 1, so we need to shift the exponent up 1. That way it all fixed itself out in the end. And so that's some nice examples of geometric series. They're very kind of explicit. They have to look a certain way. So the only other thing you could do is just manipulate the way it looks and then have to perform some sort of algebra to shift terms around so that it fits the AR to the N where N starts at 0. And then we're all in good shape and can use that shortcut. But the main two things with geometric series is what is your R value? Is it less than 1? Good. It converges. If it's not, it diverges. And not only that, if you want to tell me the sum of the series, It's very important that it looks the way it's supposed to, AR to the n, and that the index starts at 0. If it starts anywhere else, we just have to adjust it appropriately, do some algebra. So those are the two special types of series. So telescoping and geometric. Those fit the criteria of, hey, we have a way to find that formula for the nth partial sums, and therefore can talk about the convergence or divergence of these types of series. In general, finding formulas for the nth partial sums is too challenging, so we want to go about it a different way. We want to figure out, okay, maybe I can't find a formula for the nth partial sum. Is there still a way I can determine whether or not the series converges? And that's what the next couple sections are going to address. They're going to say, okay, forget the whole nth partial sum thing. Let's see if we can answer this question a different way. We'll still get the answer of convergence or divergence. We may not ever know what the sum then is, right? Since we don't have a formula for the partial sums, I may not be able to know the actual sum of the series, but I will know whether or not it's finite. Maybe I don't know what it sums to, but I do know if it sums up to something, if it's finite or infinite. And so that's going to be kind of our quest in the next couple sections. But other than that, right, we'll come back, we'll revisit series. We're going to be on the topic of series for the remainder of chapter 9, our application of sequences into series, and it should be an interesting adventure where we're going to answer all sorts of wonderful questions about adding up infinitely many things and hopefully getting something finite.